Hello, my curious friend, and a very warm welcome to Deep Field Channel. Tonight we are going to ponder one of the most unsettling yet utterly captivating revelations astronomy has ever handed us: the notion that the most monstrous black holes in the cosmos might have existed even before the galaxies that housed them, as if a heart began beating before the body was even formed. I promise to make this cosmic mystery gentle enough for your mind to drift away as you listen, though I can't guarantee a thing, because the universe rarely cooperates when it comes to being dull. But before we embark on this journey to the very edges of time, I would love to know in the comments which corner of the globe you are tuning in from tonight. If sleepiness has already overtaken you, just leave a simple hello. That tiny gesture tells the algorithm that this is a welcoming space, and it helps us bring more weary minds here to relax with us. If you enjoy our nightly scientific journeys, please leave a like and subscribe to the channel. And to those of you who have been part of this community for a while, my sincere thanks for sticking around. If you wish to get even closer, consider becoming a channel member. Members get early access to videos before anyone else, and it is a beautiful way to become part of this ongoing story. The link is right down in the description. Now, wherever you happen to be, find a truly comfortable position. Let your body sink deeply into whatever is supporting you. If sleep arrives, simply accept the invitation. Let us begin. There is an experience almost all of us have shared on some clear, cloudless night, far from the glare of city lights, when we gaze up at the sky and feel that peculiar blend of awe and slight unease, as if the vastness above is simply too immense to fit within our eyes. The Milky Way spills out like a river of spilled milk, the stars twinkle with a patience that puts us to shame, and we just stand there motionless, feeling that the heavens are eternal, fixed and ancient in a way our words struggle to properly capture. Yet what we rarely realize in that moment of stargazing is that we are actually looking into the past. Every single point of light represents a journey that photons undertook for years, decades, centuries, or even billions of years before finally reaching our retinas. The night sky is not a portrait of the universe as it is right now. It is an archive, a living museum where every layer of distance corresponds to a different slice of time. And it is precisely from this ability to peer into the past that one of the most unsettling questions in science was born, formulated with actual instruments rather than mere philosophical musing. When the James Webb Space Telescope started beaming back its first detailed pictures of the deep universe, astronomers expected to confirm their existing theories. They anticipated seeing infant galaxies still in the act of forming, with chaotic and incomplete structures like rough sketches of something still being drawn. What they discovered was far stranger. They found astonishingly mature galaxies in eras when they simply shouldn't have had enough time to grow so large. And at the center of many of these, or sometimes seemingly preceding the very galaxy surrounding them, were supermassive black holes on a scale that defies everything we thought we knew about the universe's order. To grasp why this is so deeply disturbing, we first need to build a clear mental picture together of what a black hole actually is and what it means to call something supermassive. The term black hole already carries decades of distorted cinematic imagery, and before we proceed, we must carefully undo some of those misconceptions. A black hole is not a hole in the way the word implies. It is not an empty vacuum punctured into the fabric of space like a tear in a piece of cloth. On the contrary, it is an extraordinary concentration of mass compressed into such a minuscule volume that the resulting gravity becomes inescapable for absolutely anything, including light. And it is this detail about light that makes everything so counterintuitive, because light is the fastest thing in the known universe, and yet even it cannot break free. Picture yourself standing atop a hill throwing a stone horizontally. The stone travels far, but Earth's gravity bends its path until it eventually hits the ground. Now imagine throwing that stone faster and faster. At a certain point, if you launched it with enough speed, it would curve all the way around the Earth and return right to you. That is essentially the concept of escape velocity, the speed an object must reach to break free from a celestial body's gravitational pull. For Earth, that speed is roughly 11 kilometers per second. For a black hole, the escape velocity exceeds the speed of light itself. And since nothing in the cosmos travels faster than light, nothing can possibly escape from inside a black hole once it crosses an invisible boundary known as the event horizon. This event horizon is not a physical surface. You wouldn't crash into it like you would a brick wall. It is simply the mathematical threshold beyond which gravity dominates so utterly that returning becomes impossible. An astronaut falling toward a black hole from afar wouldn't see anything special marking this boundary. From their perspective, the horizon would be invisible, indistinguishable from the surrounding space. But from the viewpoint of an outside observer, the astronaut would appear to slowly freeze in time as they approached this limit, like an image being paused, increasingly stretched and reddened by the brutal gravity until fading away completely. Time and space behave in profoundly different ways near a black hole, and this detail matters immensely for everything we will explore tonight. Black holes exist across vastly different scales. The so-called stellar mass black holes are born when massive stars reach the end of their lives and collapse in on themselves. A star with many times the mass of our Sun can, upon exhausting its nuclear fuel, collapse so rapidly that the matter at its core finds nothing to support it, and all that mass plunges inward upon itself in fractions of a second. What remains is an object with the mass of a few suns compressed into a sphere just a few kilometers in radius. That is already extraordinarily dense. But the black holes that James Webb discovered in the early universe belong to an entirely different category, one dubbed supermassive, and that prefix is no poetic exaggeration. It is a literal description of something the human language has not yet learned to comfortably measure. A supermassive black hole can harbor the mass of millions or even billions of entire suns, crushed into the center of a galaxy. The one sitting at the heart of the Milky Way, our cosmic home, is called Sagittarius A star, and it holds the mass of roughly 4 million suns. 4 million stars just like our Sun squeezed into a volume smaller than our inner solar system. Now, around certain distant galaxies that James Webb has observed, scientists have found black holes with masses of hundreds of millions or even billions of suns existing in epochs when the universe was less than a billion years old. For such a young cosmic infant to possess such a monstrously huge heart is something that simply shouldn't be possible according to the models we've built over decades of theory and observation. To truly feel the scale of this problem, it helps to think about how long it takes for things to grow in the cosmos. A star like our Sun takes tens of millions of years just to finish forming from a cloud of gas and dust. After that, it burns for billions of years before dying and potentially collapsing into a stellar black hole. For a stellar black hole to grow to a supermassive scale, conventional theory imagines it must devour gas, stars, and other material over immensely long periods, or that smaller black holes must merge in complex sequences of gravitational collisions across cosmic geological eras. Any of these processes takes time, a lot of time, and the early universe, with less than a billion years under its belt, simply wouldn't have had enough time to allow for these conventional pathways. The universe is currently about 13.8 billion years old. Less than a billion years represents just over 7% of its entire current history. It would be like finding a person with the appearance and cognitive abilities of a 60-year-old adult, yet they have only been alive for 4 years. Something in that picture just doesn't add up. Something fundamental is missing from the equation. And it is exactly this gap, this baffling discrepancy between what theory predicted and what James Webb observed, that is forcing astrophysicists to rethink some of the most basic hypotheses about how the universe organized itself in its very first moments of existence. The James Webb Space Telescope isn't the first observatory to peer into the distant universe. Its most famous predecessor, Hubble, also plunged into the cosmic depths and revealed galaxies from incredibly remote epochs. But there is a fundamental difference between the two that explains why Webb is uncovering what Hubble couldn't see with the same clarity. It has to do with the nature of light and something called cosmological redshift. When a galaxy is extremely far away, the space between it and us is expanding, which stretches the wavelength of the light it emits during its long journey to our detectors. Light that left as visible light reaches us as infrared light, shifted to longer wavelengths that the human eye cannot detect. Hubble was designed to work primarily with visible and ultraviolet light, which limited its ability to see objects very far back in time. James Webb, on the other hand, was built specifically to capture infrared light with unprecedented sensitivity. Its mirrors are much larger, its orbit takes it much further from Earth, and it operates cooled to temperatures near absolute zero to prevent its own heat from interfering with the delicate signals it collects. The result is a cosmic eye that can see galaxies that existed when the universe was only a few 100 million years old, with a sharpness that was previously impossible. And what this eye is revealing is rewriting entire chapters of cosmology. Among the most surprising discoveries is that many galaxies in the very young universe appear far too mature. Not just the galaxies themselves, but the black holes residing in their centers, or which perhaps arrive before the galaxies themselves even consolidated around them. This latter hypothesis, that black holes might have preceded galaxies, is one of the most radical inversions in recent cosmology. All the logic we constructed throughout the 20th century assumed galaxies came first. Gas clouds undergoing gravitational collapse, star formation, evolution over billions of years, and eventually, within mature galaxies, the slow accumulation of a supermassive black hole at the center. It was a clean causal narrative, reassuring in its logic of cause and effect. James Webb is suggesting that this narrative might be inverted, or at least profoundly incomplete. Some of the objects it has observed show signs of an active supermassive black hole devouring matter and shining fiercely in regions of space where the surrounding galaxy is still faint, underdeveloped, almost embryonic, as if the heart formed first and the body was built around it later, as if the gravity of the black hole was not merely a consequence of the galaxy, but the very seed that drew it into existence. This fundamentally changes how we think about large-scale cosmic structure. The universe is not a random collection of stars scattered through space. It has an architecture, a colossal web of gas and dark matter filaments where galaxies cluster at nodes, groups, and superclusters. This web began forming from the very first instance after the Big Bang, originating from tiny density fluctuations that cosmic inflation amplified and spread throughout the young space. Dark matter, which emits no light but exerts gravity, began to clump together first, creating invisible gravitational wells, where ordinary gas, the kind that forms stars and galaxies, began to flow and accumulate. Deep within these profound gravitational wells, conventional theory stated that the gas cooled, fragmented, and formed stars in large clusters. These stars formed the first primitive, irregular, and chaotic galaxies, which later merged with one another over eons, growing and becoming the spiral and elliptical galaxies we know today. The supermassive black hole supposedly grew within these developing galaxies, fed by the dense gas falling toward the center. It was a top-down story, from the larger to the smaller, from the galaxy to the black hole. But what James Webb found suggests that perhaps, in at least some cases, the story might have been bottom-up, or more accurately, inside-out. The black hole first, or at least the black hole growing so rapidly in the earliest instance that the surrounding galaxy could barely keep up. For this to be possible, there would need to be a black hole formation mechanism that doesn't rely on the slow collapse of stars over generations. There would need to be a way to create extraordinary mass concentrations much faster than conventional theory allows. And this is where the physics of the early universe begins to offer some fascinating hypotheses, ideas involving the direct collapse of massive gas clouds without passing through an intermediate star formation stage. Imagine a hydrogen cloud with the mass of 100,000 or a million suns, sufficiently isolated from cooling sources that would normally cause the gas to fragment into smaller pieces. Without this fragmentation, the entire cloud could collapse all at once, creating an object called a supermassive star, unstable and incredibly short-lived, which would immediately collapse into a black hole far larger than any conventional stellar collapse could produce. This type of object has been dubbed a heavy seed, in contrast to the light seeds that would be black holes from ordinary stars. And the difference in starting point would be enough to explain why, with just a few 100 million years of subsequent growth, these primordial black holes could already reach the supermassive scale that James Webb is observing. The universe is telling us, through the extraordinary images from this telescope floating in orbit 1.5 million kilometers from Earth, that our stories about the origin of things were far too simplistic, that the order we imagined, galaxy first, black hole later, might be more of an assumption than a fact, that there is something in the very first instance of the cosmos that we still don't fully understand, something that produced structures at scales and speeds our models still cannot faithfully replicate. And as we gaze at these primitive galaxies captured by Webb's infrared sensitivity, as we try to measure the mass of black holes that existed when the universe was still a cosmic baby, a question naturally arises that goes beyond the mechanics of formation and touches something more fundamental about the nature of the cosmos itself. Not just how these objects formed so quickly, but where the energy capable of fueling such a colossal process would come from, where the power necessary to forge gravitational colossi would originate before the universe even had time to build the structures we thought were their natural cradles. The question isn't simple to answer because the answer isn't simple to accept. When we ask where the energy comes from to forge a supermassive black hole before the universe had built a galaxy around it, we are touching on something physics understands very well in principle, but which still faces an abyss when trying to apply that knowledge to the scale and speed the Webb telescope has shown us. The energy exists, the laws governing it exist. The problem is that the combination of quantity, time, and location still resists a completely satisfying explanation. Imagine a waterfall, not a small one, just a few meters high, but a colossal drop where billions of tons of water plunge from an absurd height. As the water falls, it carries kinetic energy, the energy of motion, and this energy has to go somewhere when the flow finally meets resistance at the base. Some turns into heat, some turns into sound, some agitates the rock below. Nothing is lost, everything is transformed. Now replace the water with gas, with cosmic dust, with primordial hydrogen gathered by gravity across distances we can barely fathom, and you have the basic principle of what feeds a growing black hole. Matter falls. And when matter falls toward a point of extreme gravity, the universe collects its tribute in energy. This process has a name, it's called accretion. And it is, without exaggeration, the most energetically efficient process physics knows in the observable universe. When a piece of matter spirals toward a black hole and crosses the event horizon, a substantial fraction of its mass is converted into pure energy before vanishing forever. To compare it to something familiar, nuclear fusion, the process that powers the Sun and all cosmic stars, converts less than 1% of its mass into energy. Accretion around a spinning black hole can convert between 10 and over 40% of mass into energy. The difference between these values isn't marginal. It's the difference between a candle and a lightning bolt. There is a physical reason for this absurd efficiency, and it lies in the curvature of space itself. As matter approaches a black hole, it doesn't fall in a straight line, because nothing in the universe falls straight down into a spinning object. It begins to orbit, and as it orbits closer and closer, the orbits become smaller and faster. What forms is what we call an accretion disk, a flat, brilliant structure of superheated gas spinning around the black hole like water circling a drain, only at temperatures of tens of millions of degrees. It is in this disk that energy is extracted. Friction between layers of gas spinning at slightly different speeds generates heat. The heat generates radiation. The radiation escapes, and some of it can be detected by telescopes billions of light years away. But what exactly is being converted into energy in this process? The answer touches on one of the deepest laws of the cosmos, the conservation of energy, which tells us that energy cannot be created or destroyed, only transformed. What happens during accretion is a conversion of gravitational potential energy into kinetic energy, and then into heat and radiation. The deeper into the gravitational well the matter falls, the more energy can be extracted from that plunge. And the gravitational well of a supermassive black hole is the deepest nature allows to be built. This means that the universe, by creating massive black holes at the dawn of time, also created the greatest power plants that have ever existed. This realization didn't arrive all at once. It was built over decades of frustrated observations, abandoned hypotheses, and intuitions that took years to formalize. In the early 20th century, physics had the mathematical tools to describe intense gravitational fields, but the idea that an object could be so dense that not even light could escape its surface remained in the realm of theoretical exercise, almost a curiosity. It was only with the solutions to Einstein's general relativity, explored in depth by Karl Schwarzschild while still serving during the First World War, that the concept gained rigorous mathematical grounding. Schwarzschild was in the trenches of the Eastern Front when he solved Einstein's field equations and mailed the solution weeks before his death. His solution described the space around a spherically symmetric mass and revealed something unsettling. There was a critical radius below which no information, no particle, no photon could escape. For decades, however, most physicists treated this solution as a mathematical singularity with no counterpart in physical reality. Einstein himself doubted such objects could exist. It took observational astrophysics maturing and radio telescopes beginning to pick up signals from quasars in the 1960s for the bridge between mathematics and the real sky to start being built. Quasars were disturbing objects. They looked like stars in the sky, hence the name derived from quasi-stellar, but they radiated energy equivalent to hundreds of entire galaxies from a region the size of our solar system. Nothing in the theories of the time could explain how such a compact object could produce so much energy. It was Donald Lynden Bell who, in the late 1960s, articulated the mechanism with clarity. In a paper that became a landmark in the history of astrophysics, he proposed that quasars were powered by supermassive black holes at the centers of distant galaxies, and that the accretion process was the energy source. The idea was elegant, it was correct, and it took decades to be widely accepted. The skepticism was understandable. Accepting that the universe contained objects of millions or billions of solar masses compressed into a tiny region required a profound revision of how we thought about the structure of matter and the limits of what nature allows to be built. As acceptance grew, so did the question of how these objects formed. And here we enter territory where physical laws reveal themselves as both tools and obstacles. The law of conservation of angular momentum, for instance, is simultaneously the reason the accretion disk exists and one of the main reasons a black hole's growth cannot simply be limitless. When matter begins falling toward a gravitational point, it carries with it whatever rotation it already had. And because angular momentum must be conserved, the closer this matter gets to the center, the faster it begins to spin. Like a figure skater pulling in their arms and accelerating on their axis, the gas spiraling inward spins ever faster, and this rotation creates resistance. The matter cannot fall straight in. It must lose angular momentum somehow to continue falling. This mechanism for losing angular momentum was a puzzle for many years. The normal viscosity of the gas was completely insufficient to explain the accretion rates observed in quasars. It was only with the work of Stephen Balbus and John Hawley in the early 1990s that the solution emerged convincingly. Magnetorotational instabilities in the accretion disk's plasma created turbulence efficient enough to transport angular momentum outward, allowing matter to continue falling inward. The magnetic field, which permeates practically everything in the universe, played a central role not just in confining matter, but in moving energy and momentum in a way classical physics hadn't captured. And the magnetic field leads us to another piece of this energetic puzzle that appears repeatedly when we study black holes: relativistic jets. Many supermassive black holes in intense accretion phases don't just swallow matter and radiate light from the disk. They also produce columns of plasma, accelerated to speeds nearing that of light, fired perpendicularly to the disk's plane, like two cosmic lighthouses pointing in opposite directions. These jets can extend for hundreds of thousands of light years, far beyond the limits of the host galaxy itself, carrying enormous amounts of energy and momentum into the intergalactic medium. The exact mechanism of jet formation still has debated aspects, but the contribution of the spinning black hole's magnetic field, described by the process we call the Blandford-Znajek mechanism, is now considered fundamental. The spinning black hole acts as a cosmic gyroscope of energy. Its rotation, described by the Kerr solution to Einstein's equations, creates a region around it called the ergosphere, where space itself is dragged along with the object's rotation. Matter entering the ergosphere can, in principle, extract energy from the black hole's spin itself, a process called Penrose extraction. The universe allows, under certain conditions, for the rotational energy of a black hole to be stolen by the surrounding matter. It isn't a violation of energy conservation. It is energy conservation operating in a regime where space-time itself is a reservoir of rotational energy. All this physics, accretion, angular momentum transport, jets, the ergosphere, the Blandford-Znajek mechanism, was developed over decades and built upon observations of black holes we find in the relatively late universe. They were objects that had enough time to develop within mature galaxies, surrounded by matter from known sources. The challenge Webb poses to this well-established physics is radical. It must work not in a tranquil, well-supplied environment, but in the early universe, when everything was hotter, denser, more turbulent, and when the available time was only a minuscule fraction of what we imagined necessary. In the primordial universe, gas was abundant. The cosmos was filled with hydrogen and helium, the elements forged in the first minute after the beginning of everything. This gas wasn't distributed perfectly homogeneously. Quantum fluctuations from the inflationary period had left subtle marks on the matter distribution, slightly denser regions and slightly rarer ones. In the denser regions, gravity began to work, pulling more and more gas inward. This is the seed of all the structure that exists in the current cosmos. And if one of these regions collapses directly into a black hole before a star has time to form, or if the star that forms is so massive that the collapse is almost immediate, then the gravitational seed is planted before anything else exists around it. What makes the problem more acute when we put Webb's data into perspective is the required growth rate. A black hole of a few thousand solar masses formed from the collapse of a massive star or a primordial cloud would need to grow at an extraordinary rate to become a monster of billions of solar masses in just a few 100 million years. Growing exclusively through accretion, within the limits imposed by the so-called Eddington luminosity, which is the point where the radiation pressure of the accreted material equals the gravitational force and literally blows away the inflow, would make this growth extremely difficult to achieve in the observed timeframes. The Eddington luminosity isn't an arbitrary law. It's a direct consequence of the physics of photon-electron interaction, of the radiation pressure light exerts on matter. It places a natural ceiling on the sustained accretion rate for a given black hole. To grow as fast as Webb suggests, the first black holes would have needed to start with much larger masses than we expected, or they would have gone through episodes of accretion far above the Eddington limit, for periods short enough not to destroy everything around them, or both. There is also the possibility that unsettles more than one cosmologist, that the early universe had conditions that simply have no analog in the current cosmos, conditions that made gravitational collapse more efficient, faster, and more definitive than anything we can reproduce or observe today. One scenario that has gained growing attention is direct collapse. In certain regions of the early universe, where the temperature was high enough to prevent the formation of molecular hydrogen, and where therefore gas cooling was less efficient, a massive gas cloud could collapse directly into a dense object without going through a stellar phase. With no stars to explode, no supernovae to redistribute matter, the collapse would be continuous, producing a black hole of perhaps 100,000 solar masses right from the start. This would be a far more generous seed than any star could provide, but even this seed would need to grow by a factor of tens of thousands to reach the sizes Webb is finding. And here lies the fundamental imbalance that makes this process work. The early universe was dense, not dense like the interior of a star or a molecular cloud, but dense in the cosmological sense, meaning the available matter per volume was much greater than in any later era. In this environment, a black hole that started large found abundant gas on all sides. There was no galaxy to organize and regulate the flow. There were no stars exploding and sending winds sweeping the gas away. There was only gravity on one side and matter availability on the other. The imbalance is this, between the capacity to attract and the resistance to maintain. As long as the radiation pressure generated by the accreting black hole cannot expel the gas faster than gravity restores it from the surrounding reserves, growth continues. In the early universe, the reserves were virtually limitless on a local scale. The black hole grew. And growing is the simplest verb to describe a process that was actually a dance between quantum physics, general relativity, magnetism, and thermodynamics, all happening simultaneously, all feeding back into each other. Think of a small campfire in a dry forest. The fire heats the air around it, which rises. Cooler, oxygen-rich air enters from the base to replace what left. More oxygen feeds larger flames. Larger flames heat more air. The cycle feeds on itself as long as there is fuel. In a sufficiently dry and vast forest, The campfire can grow to dimensions the original fire couldn't predict. The black hole in the early universe was that spark, and the newborn cosmos was the forest. The local mechanism is this: a gravitational perturbation captures gas. The gas falls and releases energy. Part of that energy leaves as light and jets. The increased gravity attracts more gas. The black hole grows. The local scale of the process is understandable, almost intuitive. Each step follows laws we know and that have been tested in observations of nearby objects. There is no magic in any individual step. What is disconcerting isn't the mechanism, it's what happens when this mechanism, operating in the exceptional environment of the early universe with higher densities, higher temperatures, virtually inexhaustible local gas reserves, repeats not once, not in an isolated place, but in hundreds, perhaps thousands of points simultaneously, for tens of millions of years under conditions that will never repeat on this scale in the cosmos. What happens when this accretion cycle repeats not just locally, but across the entire cosmic tapestry at once, when each of these campfires grows large enough to influence not just its immediate surroundings, but the gas clouds that will eventually form the galaxies, stars, and planetary systems that will come much later. When one contemplates the early universe not as a collection of isolated events but as a living, interconnected system, something changes in how questions must be formulated. The question ceases to be how a single black hole grows and becomes how hundreds of them grow simultaneously, in places separated by immense distances, without any direct communication between them, and yet produce patterns that repeat with a disturbing regularity. The question becomes about the origin of order in a universe that, on the surface, seemed destined only for the chaos of the first eras. Cosmologists who study the large-scale structure of the cosmos have a name for what emerges from these initial conditions. They call it the cosmic web, and this expression, though used frequently enough to seem banal, describes something that continues to surprise every time it is observed with new instruments. The web is not a metaphor. It is a real, measurable structure with filaments of matter stretching for tens and hundreds of millions of light years, connecting nodes where density is highest, separated by voids where matter is scarce to the point of near absence. This structure wasn't drawn by anyone. It emerged from the most fundamental physics, from quantum fluctuations that existed before there were even stars, black holes, or galaxies. The story of the web begins before the universe had any visible structure. In the very first instant after the beginning, the cosmos was a place of near-perfect uniformity, a hot, dense fog where matter was distributed so homogeneously that any equally sized cross-section would contain practically the same amount of energy. But the near in that phrase carries all the weight of what would come later. There were minuscule fluctuations, density variations on the order of 1 part in 100,000, which were the amplified echo of quantum processes that occurred in unimaginably small fractions of a second. These fluctuations were the initial code of the cosmos, the instructions from which all existing structure would be built. Gravity is patient and relentless. Where there was a region slightly denser than the surrounding environment, gravity pulled more matter toward it, making it even denser, which increased its gravitational pull, which brought in even more matter. The process is the same one that operates on all scales of nature, from crystal growth to planet formation. What makes it special on the cosmic scale is the time available and the amount of matter at play. For hundreds of millions of years before any starlight illuminated the universe, gravity worked in silence, sculpting the original chaos into increasingly elaborate structures. The result of this process wasn't a random distribution of matter, it was exactly the web that telescopes reveal today. The filaments we observe when mapping the distribution of galaxies in the local universe are the direct descendants of these primordial fluctuations, grown and amplified over billions of years. And the nodes of the web, the places where multiple filaments meet, are the densest environments in the cosmos, the places where matter accumulation was most intense and earliest. They are, therefore, the places where the first massive black holes formed with the greatest ease. There is a geometry in this distribution that goes beyond mere density. The filaments aren't amorphous objects. They have preferential directions, curvatures that reflect the flow of matter along pressure and gravity gradients that existed since the first instance. Matter didn't simply fall into the nodes like rain falls vertically. It flowed along the filaments like water in cosmic rivers, converging at the nodes from specific directions determined by the web's geometry. This flow geometry had consequences for what happened to the gas when it reached the nodes. When gas flows arrive from different directions and meet at a point, they carry angular momentum. If the flows arrived from perfectly opposite directions in perfectly equal amounts, the angular momentum would cancel out. But the real universe isn't that symmetrical. The filaments differ in thickness, in flow speed, in composition. The gas converging at the nodes arrives with a residual rotational asymmetry, and this asymmetry becomes the germ of the rotation of the structures that form. It's the reason galaxies spin. It's the reason accretion disks spin. It's the reason angular momentum is a fundamental property of almost everything that exists on astronomical scales. For the black holes forming in the nodes of the primordial web, this rotational heritage had profound implications. A spinning black hole carries a property called the spin parameter, which describes how rapidly it rotates relative to the theoretical maximum allowed by the laws of physics. A black hole with high spin has an ergosphere, a region around it where space itself is dragged in the direction of rotation, where nothing can remain stationary relative to the distant universe. This region of dragged space has unique physical properties that dramatically affect how gas falls into the black hole and how much energy is released in the process. The efficiency with which a spinning black hole extracts energy from the gas falling toward it is substantially higher than the efficiency of a non-spinning black hole. This means that, all other conditions being equal, a rapidly spinning black hole will grow differently, release more energy per unit of accreted mass, and have a greater impact on the surrounding gas than a black hole that doesn't spin. And because the spin of primordial black holes depended on the geometry of the flows feeding them, and this geometry was determined by the large-scale structure of the cosmic web, there was a direct connection between the large-scale organization of the universe and the individual properties of the black holes growing in its nodes. This connection between cosmological scale and the properties of individual objects is one of the most fascinating aspects of modern cosmology. It means that a specific black hole in the early universe wasn't just a local object formed by local conditions. It was also the product of processes operating on much larger scales, the convergence point of flows that had their origins in the quantum fluctuations of the cosmos's first instance. Each primordial black hole was, in a sense, a summary of the entire history of the universe up to that point, compressed into an object of minuscule dimensions relative to the scales that created it. Vera Rubin, before her passing, had dedicated decades to studying galaxy rotation and the problem of dark matter. Her work established that galaxies spin in ways that cannot be explained solely by the visible matter they contain. There is more mass than meets the eye, distributed in extensive halos that envelop galaxies and govern their dynamics. The dark matter that Rubin helped establish as a fundamental component of the cosmos is also an essential ingredient in the formation of primitive structures. Its halos were the gravitational wells where gas accumulated, and its distribution followed the same web as the luminous gas, but even more pronouncedly, because dark matter interacts only gravitationally and doesn't dissipate energy through radiation. Rubin's contribution to understanding the present has a direct echo in the questions James Webb raises about the past. If dark matter dominates galaxy dynamics today, it dominated the dynamics of primitive structures even more completely, before ordinary matter had time to concentrate and form stars and black holes in sufficient quantities to exert its own significant influence. The first massive black holes grew within dark matter halos that preceded them and defined the gravitational wells where gas accumulated. The matter that emits no light and cannot be seen directly was the invisible scaffolding upon which the entire visible structure of the cosmos was built. When astronomers began mapping the distribution of quasars in the early universe, they found something that, in retrospect, shouldn't have been surprising but still made an impression. Quasars weren't distributed randomly. They traced structures. There were regions of the young universe where quasars clustered in concentrations that revealed the nodes and filaments of a web that existed when the cosmos was only a small fraction of its current age. The coincidence between quasar distribution and the expected distribution of high-density nodes was too precise to be casual. Quasars were exactly where you'd expect to find them if they were tracers of the most massive black holes, and the most massive black holes were exactly where you'd expect to find them if they grew preferentially in the densest environments of the cosmic web. This correspondence allowed something valuable for cosmologists. If quasar distribution reflects the distribution of massive black holes, and if the distribution of massive black holes reflects the distribution of cosmic web nodes, then quasars can be used as markers of the large-scale structure of the early universe in a way that complements other methods. They are extremely bright beacons that light up exactly in the places where density was highest, where filaments converged, where dark matter had created the deepest gravitational wells. It's as if the young universe had placed lanterns at the most important points on its map. The idea that large-scale structure and the properties of individual objects are connected through the physics of structure formation is known as formation bias. More massive objects tend to form in denser environments because these environments provide more material and because the density fluctuations that created them were more intense. This means the most massive black holes in the early universe weren't distributed randomly among all available halos. They were concentrated in the most massive halos, which in turn were concentrated in the densest nodes of the web. The mass distribution in primordial black holes was even more concentrated than the total mass distribution, with a disproportionately large share of black hole mass residing in a relatively small number of extremely massive objects in extremely dense environments. Martin Rees, the British cosmologist who dedicated decades to understanding the extreme environments of the universe, proposed decades ago that supermassive black holes could be the central engines of quasars and active galactic nuclei. When this idea was proposed, it seemed audacious. Today it is established consensus. But what makes Rees's work relevant to the question of large-scale organization is his emphasis on the role these central engines play, not just as isolated objects but as agents of transformation for their surrounding environment. A black hole accumulating mass isn't passive. It responds to the universe around it, and the universe responds to it. And this reciprocity is what creates patterns that no individual component planned. When multiple black holes grow simultaneously in adjacent nodes of the cosmic web, their influences overlap in ways that aren't simply the sum of individual influences. The gas in the filaments connecting two adjacent nodes can be heated by the energetic processes of both black holes at the same time. A filament that under normal conditions would supply cold gas to both nodes can become a channel of hot gas that slows the growth of both. The interaction isn't direct, it doesn't involve communication between the black holes. It involves mediation by the gas filling the space between them, and this gas is affected by everything happening in its vicinity. This gas-mediated interaction creates correlations between black holes separated by distances far greater than any direct interaction could reach. It's a type of non-local communication operating through the physics of gas, thermodynamics, and hydrodynamics. When astronomers observe that black holes in dense environments grow differently than black holes in less dense environments, they aren't just observing the effect of locally available gas. They are observing the accumulated product of these mediated interactions stretching across the Webb's filaments. The large-scale organization emerging from these processes has a hierarchy of scales that is one of the hallmarks of complex physical systems. There are patterns on the scale of megaparsecs, the great filaments and nodes of the Webb. There are patterns on the scale of kiloparsecs, the internal structures of the halos where black holes grow. There are patterns on the scale of parsecs, the immediate regions around the black holes where accreting gas interacts with the radiation and winds the black hole emits. Each scale influences the others through specific physical processes, and a complete understanding of the system requires understanding how these scales fit together. This hierarchy of scales motivated the development of large-scale cosmological simulations that have become central tools in astrophysics over the last few decades. Projects like Millennium, Illustris, Eagle, and TNG, each with its own set of physical ingredients and choices on how to model processes occurring on scales smaller than the simulation's resolution, all seek to capture this hierarchy comprehensively enough to reproduce the universe we observe, and all of them incorporate black holes as essential ingredients. Without black holes, simulations produce galaxies that are too massive, too cold, and too bright. With black holes modeled properly, the galaxies emerging from the simulations resemble the galaxies telescopes observe. This need for black holes in simulations to reproduce galaxy properties is indirect but powerful evidence of the role they play in the large-scale organization of the cosmos. If black holes didn't influence galaxy formation, we could remove them from simulations without losing anything important. The fact that we can't, that their absence produces a universe that doesn't look like what exists, says something profound about their importance as organizers of cosmic structure. The universe James Webb observes, when looking at the first few 100 million years of cosmic existence, isn't a universe of isolated objects doing isolated things. It is a universe of interactions, flows, and influences that cross scales and connect the behavior of individual objects to the global architecture of the cosmos. The black holes Webb detects, which exist before the galaxies that will eventually envelop them, are nodes in a web of causality connecting the quantum fluctuations of the first instance to the structured universe we see billions of years later. There is a particular beauty in the idea that the order we observe wasn't planned by any of its components. No dark matter particle knew it was creating the scaffolding for a galaxy. No hydrogen atom falling toward a proto-black hole knew it was contributing to a process that would eventually shape the distribution of galaxies across a multi-megaparsec region. Order emerges from interactions, from physics operating consistently across all scales, from geometry imposing constraints on the movement of matter. It is an order that needed no intention to exist, and which is therefore even more impressive. What becomes evident when contemplating this multi-scale organization is that the existing patterns would look very different in the absence of something that amplifies them. The web would exist anyway. Filaments would form, nodes would accumulate matter, dark matter halos would create the gravitational wells where gas would concentrate. But the intensity of the contrasts, the depth of the differences between the densest and least dense environments, the speed at which certain regions became dominant over others, the ability of certain nodes to influence distant filaments in a way nodes without that specific ingredient couldn't. All this points to the presence of an amplifying factor whose absence would make the universe a smoother, more gradual structure, less articulated in its differences. This amplifying factor is the central black hole, not as a symbol, not as a convenient metaphor for chaos or destructive power, but as a real, measurable physical mechanism, endowed with properties that make it capable of acting on scales much larger than the volume it occupies. The idea that something so compact can reorganize the destiny of a structure millions of times larger than itself is one of the most unsettling conclusions modern astrophysics has come to support with solid evidence. And the disturbance isn't merely emotional, it's conceptual. It challenges the basic intuition that an object's influence must be proportional to its visible size. The supermassive black hole inhabiting the center of a galaxy occupies not even a minuscule fraction of that galaxy's total volume. If you imagine the Milky Way as a continent, the black hole at its center would be smaller than a grain of sand. Less than that, depending on the scale you chose for the comparison. This disproportion is what makes the phenomenon so hard to accept intuitively. We are conditioned by all everyday experience to expect that the large affects the small, that the powerful is also voluminous, visible, and imposing in its dimensions. The black hole completely shatters this expectation and does so in a way that is neither metaphorical nor philosophical, but rigorously physical. The mechanism by which this amplifier acts on the surrounding galaxy is called active galactic nucleus feedback. When the central black hole is in an active accretion phase, meaning it's consuming matter intensely, it doesn't just absorb, it emits, and what it emits is of an intensity that rivals or exceeds the combined emission of all the billions of stars in the host galaxy. The accretion disk forming around the black hole as matter spirals toward it heats to extraordinary temperatures. Friction between layers of gas in slightly different orbits generates energy that has to go somewhere. Some goes into producing light across the entire electromagnetic spectrum, from radio to gamma rays. Some goes into generating jets. Jets are perhaps the most visible and dramatically asymmetric manifestation of the black hole's amplifying power. They are columns of magnetized plasma emerging from the poles of the accretion system at speeds approaching that of light, not approaching the speed of light in a casual, approximate way, like any fast object nearing some limit. At speeds reaching over 95% of the speed of light, in some cases recorded and measured precisely by radio telescopes. These jets travel hundreds of thousands of light years out of the galaxy. They pierce the galactic halo, penetrate the intergalactic medium, and when they finally lose coherence and disperse, they form enormous structures called radio lobes that can extend for several megaparsecs. A megaparsec is a distance that requires a moment of contemplation to process. It equals over 3 million light-years, and there are galaxies whose jets from the central black hole produce lobes spanning several megaparsecs, structures larger than the distance separating neighboring galaxies in moderately dense groups. The black hole, that grain of sand in the galactic continent, created a structure exceeding the galaxy's own size by multiple orders of magnitude. This isn't a peripheral curiosity of astrophysics. It's a central fact about how the universe organizes itself on a large scale. Feedback happens because these jets, and also the wind of particles and radiation the active galactic nucleus emits in all directions, interact with the gas surrounding the galaxy that would normally be the material from which new stars form. When this gas is heated by the black hole's energy, or when it's swept out of the galaxy by the momentum of the jets, it becomes unavailable to collapse and form stars. the galaxy's star formation rate drops. In extreme cases, the galaxy can have its cold gas supply virtually eliminated, transforming it from a young, blue, active, and growing structure into an old red, quiescent, and demographically declining one. This process has a name in cosmological models: quenching, the suffocation of the galaxy by its own nucleus. The word quenching comes from metallurgy vocabulary, where it describes the rapid cooling of heated metal to alter its properties. In cosmology, the meaning is opposite in terms of temperature, but analogous in terms of consequence. The black hole heats and disperses the gas that would feed the galaxy, and this heating acts as a cooling of galactic activity. There's an elegant irony in this nomenclature that the field adopted almost without noticing. The amplifier, in its most intense phase, can transform into an extinguisher, and the galaxy that grew the most, that accumulated the most massive black hole, that had the most active nucleus, might be exactly the one that earliest ended its capacity to generate new generations of stars. The observable manifestations of this process have a beauty accessible even to instruments less sophisticated than James Webb. Quasars were the first objects in which humanity recognized, even without initially understanding what it was seeing, the signature of a supermassive black hole in full accretion activity. The word quasar is a contraction of quasi-stellar radio source. When the first radio astronomers in the second half of the 20th century began mapping the sky in radio waves, they found point sources of intense emission that, when investigated with optical telescopes, looked like stars. They looked like stars, but something was wrong. Their positions corresponded to objects whose light spectra showed immense redshifts, indicating they were at absurd distances in very ancient epochs of the universe. An object that looks like a point-like star but is billions of light years away needs to emit an amount of energy no individual star could produce. The conclusion arrived gradually, with resistance and debate, but it arrived. What radio astronomers had found were entire galaxies being outshone by a single point at their centers, a point where the central black hole was consuming matter at extraordinary rates and releasing energy in quantities that made everything around it invisible by comparison. A quasar isn't an object, it's a state. It's a galaxy whose central black hole has entered a maximum accretion phase and whose central luminosity has surpassed all its combined components. This understanding changed how astronomers interpreted the sky. Objects catalogued as peculiar stars for decades were reclassified. The catalog began to be read with new eyes, and some of the most intense radio sources in the sky revealed themselves to be galaxies at distances corresponding to the universe at less than 1 billion years old, sometimes even less. This meant the supermassive black holes fueling them already existed at that time, had already accumulated masses of hundreds of millions or billions of times the Sun's mass, and were already active and influential much earlier than any model of the time could explain. Seyfert galaxies are a neighboring category in the taxonomy of active galactic nuclei. The name comes from Carl Seyfert, who in the early decades of the 20th century identified spiral galaxies with unusually bright nuclei and emission spectra, revealing gas moving at extremely high speeds around the center. Seyfert galaxies are lower intensity quasars, or quasars in a less extreme stage of activity, where the nucleus's contribution is intense but not enough to completely erase the host galaxy's light. In the best telescopes, you can see the spiral structure around the bright nucleus. You see the galaxy and its amplifier simultaneously. There are two classic types of Seyfert galaxies. In Type 1, the spectrum shows very broad emission lines produced by fast-moving gas very close to the black hole in the broad line region, where speeds of thousands of kilometers per second broaden the lines via the Doppler effect as well as narrower lines from more distant regions. In type 2, the broad lines are absent or weakened in the observed spectrum, not because that region doesn't exist, but because it's hidden by a torus of dust and gas surrounding the black hole in a plane perpendicular to the jet axis. This discovery that the two types were likely the same phenomenon viewed from different angles was a revealing moment about how observation geometry can create classifications that seem profound but are merely perspectives. The dust torus is itself a fascinating structure. It's a ring of dense material encircling the black hole, an accretion disk on a scale of a few parsecs, sometimes tens of parsecs. It's opaque to visible light but transparent to infrared and radio wavelengths, allowing telescopes like James Webb, which operates primarily in the infrared, to see through it and observe structures that would be completely obscured to an optical telescope. This property of James Webb isn't a minor technical detail. It's the reason it was able to fundamentally alter what we know about the early history of black holes and galaxies. It sees where previous instruments were blind. Blazars are the third major type of active galactic nucleus worthy of contemplation for their extreme position in the spectrum. The name is a combination of Bl Lacertae, the class prototype, with the quasar ending. Bl Lacertae was catalogued for decades as a variable star in our own galaxy before redshift measurements revealed it was at an immense distance. It's a blazar, a galaxy whose central black hole is emitting a jet directly in our direction. When the jet points at the observer, the emitted radiation undergoes a phenomenon called relativistic beaming that amplifies its intensity by factors that can reach thousands. What we see isn't isotropic emission in all directions, but the emission of a focused beam that accidentally points at us, like looking directly into a lighthouse in the dark. Blazars are the most variable objects known in the universe. Their luminosity can double in hours or minutes because the variation doesn't reflect changes in the black hole's accretion, which would happen on much larger timescales, but turbulence within the relativistic jet disturbing the emission's coherence. You can imagine observing a candle flame from a great distance and trying to infer what happens inside the engine producing it from the rapid fluctuations in its intensity. That is the task of the astronomer studying blazars, inferring the physics of the black hole and accretion disk from the chaotic and magnified behavior of the jet stretching toward them. There's an invitation in this plurality of forms. When you look at the sky on a clear night and see the band of the Milky Way, you're looking at a galaxy in whose central direction lies Sagittarius A star, our galaxy's supermassive black hole with a mass of about 4 million times the Sun's mass. It's currently in a quiescent state with low accretion activity compared to distant quasars. But there's evidence it went through more intense activity phases. Gamma-ray emission bubbles called Fermi bubbles, stretching tens of thousands of light-years above and below the galactic plane, are interpreted by many researchers as remnants of a past activity phase. The amplifier at the center of our galaxy has acted before. The marks it left are still visible to sensitive enough instruments. This makes the experience of looking at the Milky Way different when you carry this knowledge. The luminous band you see is the galactic plane, billions of stars compressed by perspective into a band of diffuse light, and at the center of that band, obscured by the dense dust of the galactic plane, invisible to eyes that only capture visible light, lies the remnant of something that shaped the entire galaxy's structure, the gas that didn't form certain stars because it was expelled, the filaments of matter around the galaxy that were reorganized by the expanding bubbles, the current distribution of dark matter in the halo carrying the gravitational memory of past phases. You aren't looking at a static scenario. You're looking at the result of a process that continues on geological and cosmological timescales unfolding. The perceptual experience of the amplifier doesn't need to be restricted to the sky. There is an everyday analogy that isn't just poetic but structurally isomorphic to the physical process. Think of how certain conversations, certain people, certain contexts act as amplifiers of tendencies that would exist anyway. An idea present diffusely in a mind can remain diffuse for years without consequence, but introduced into the right environment, connected to the right node of a social or intellectual network, it intensifies, propagates, and organizes other dispersed elements around itself. The amplifier didn't create the idea, but it completely transformed its trajectory and reach. The black hole didn't create the galaxy, but it defined what it became. This intuition isn't a loosely applied metaphor. It points to a principle that seems to work across multiple scales of organization, from physics to the social, from biology to astronomy. The presence of a highly concentrated and energetically intense node in a network distributes influence asymmetrically, and this asymmetry doesn't diminish with distance as quickly as we'd expect. The black hole's jets act on gas hundreds of thousands of light years away. A central voice in a culture can reorganize practices in peripheries that never received direct contact. The mechanism is different, but the structural logic of a symmetric amplification from a dense node resonates. What systematic observation of active galactic nuclei across different cosmic epochs reveals is a story of varying intensities. The young universe between 1 and 3 billion years after the Big Bang was the golden age of quasars. There was more accretion, more galaxy mergers feeding black holes with fresh gas, more activity in the nuclei. As the universe aged, available cold gas decreased, mergers became less frequent, and galactic nuclei mostly entered states of lower activity. Today's universe is, on average, quieter than the young universe. The amplifiers that defined existing structures are now mostly at rest, like turned off but still hot engines, keeping the surrounding environment's temperature much higher than it would be without their past presence. This rest, however, is contingent. Sagittarius A star is quiescent now, but there's matter around it. There are gas clouds orbiting the galactic center. There's the periodic passage of stars and fragments that could, under favorable circumstances, provide material for a renewed accretion episode. In neighboring galaxies, central black holes show activity in varying degrees. Centaurus A, an elliptical galaxy a few megaparsecs from us, has an active nucleus visible even in amateur telescopes, with a radio jet stretching hundreds of thousands of light years. M87, the galaxy whose central black hole image was captured by the Event Horizon Telescope in a historic image, shows a jet that has been studied for decades and remains one of the richest data sources on relativistic jet physics. What these neighboring galaxies offer us is the possibility of observing the amplifier in action with a proximity distant objects don't allow. The distance separating a quasar from us reduces it to a point of light without resolvable spatial structure. But Centaurus A and M87 are close enough that the jet's lobes and accretion regions can be mapped in detail. And what these maps show is an internal complexity that simplified models don't fully capture. Turbulence regions within the jet, intense brightness points indicating shocks, composition variations along the jet's length, suggesting the material isn't uniform over time or space. There's a state that seems like equilibrium when viewed from afar. The galaxy rotates. Stars follow their orbits. The diffuse gas around distributes seemingly stably. The central black hole remains at rest, with minimal accretion, no active jets, no emission dominating the spectrum. To an external observer with modest instruments, this galaxy looks tranquil, organized, functioning like a well-calibrated mechanism that found its rhythm. The appearance is convincing, and the universe's history, read from this appearance, would be a story of systems that grew, organized, found stability, and now simply continue. But the stability seen is built on an equilibrium that is, in a technical sense, metastable. It isn't the equilibrium of a system that reached its lowest energy state and will remain there indefinitely. It's the equilibrium of something that found a configuration that works while surrounding conditions remain roughly constant, but which can be perturbed by events that, from the system's viewpoint, are external and unpredictable. A merger with a smaller galaxy, the passage of a dense gas cloud in an orbit close to the central black hole, a cascade of star formation in a region increasing radiation pressure on surrounding gas. Each of these events can be, on a cosmological timescale, relatively simple, but can trigger a black hole response altering the galaxy in ways propagating for billions of years. Equilibrium exists, but it exists in the same way the equilibrium of a large rock on top of a gentle hill exists. Before someone realizes there's a slope, it hasn't started descending yet. The rock is stationary, that's true, but the more accurate description isn't that it's in permanent rest. It's that it hasn't yet found the trigger that will start the movement. And when that movement begins, the scale of what happens next will be determined not just by the rock, but by the entire geometry of the terrain descending below it, by every filament, every node, every structure the fall will encounter and reorganize on its way. The rock starts moving when the terrain it couldn't see yet reveals itself beneath its feet. And in the universe, this moment of revelation has no sound, no announcement, no visible signal crossing space in time to warn anyone. It simply happens, and what happens next redefines everything around it. A supermassive black hole at a galaxy's center can go through periods that, on a human scale, seem unimaginably long of relative containment. The surrounding gas falls in a spiral at a controlled pace. The released energy dissipates without accumulating enough pressure to reorganize the galaxy's structure. The system found a sort of sustainable flow where matter input and energy output balance in a way preserving existing conditions. This flow can last tens of millions of years. In cosmological terms, that's a moderate interval, but long enough for entire stars to be born, live, and die within it. What changes this state isn't a single catastrophic event from outside. What changes it is the accumulation of conditions already forming within the system, invisible in the galaxy's superficial behavior, but present in the gas geometry, filament temperatures, and densities of regions that haven't yet reached the accretion disk. An amount of cold matter begins collapsing toward the center via a path finding insufficient resistance to slow it. It arrives faster than the system was prepared to process. The accretion disk thickens. Temperature rises. Energy release increases non-linearly. Nonlinear is the word that matters here. In linear systems, doubling the input produces roughly double the output, but the active galactic nucleus doesn't work that way. When the accretion rate crosses certain thresholds, the efficiency with which the black hole converts mass into radiant energy increases so that small input variations produce enormous output variations. The system enters a different regime. It isn't simply more of the same. It's something qualitatively distinct, with its own rules, its own scales, its own ways of interacting with everything around it. Physicists studying these processes use the Eddington rate concept to describe the critical threshold. Every black hole of a given mass has a theoretical maximum accretion rate above which the radiation pressure generated by falling matter becomes strong enough to push away the very matter trying to fall in. When accretion approaches this limit, the system enters internal tension. The black hole is trying to swallow matter faster than physics allows without consequences. Something has to give, and what gives is the flow geometry, collapsing into dramatically different modes than before. One of the most extraordinary results of this geometry collapse is the formation of relativistic jets. They are structures remaining among the most violent and enduring the universe produces. When the magnetic field around the black hole becomes sufficiently organized and the accretion rate high enough, energy that can't be absorbed by the event horizon is channeled through the system's poles into plasma beams moving at speeds approaching light. These jets aren't ephemeral. They can persist for hundreds of millions of years. They can extend for distances exceeding the host galaxy's size by a factor of tens, reaching the sparsest regions of the intergalactic medium. Inside these jets, charged particles are accelerated to energies no human-built accelerator can reproduce even on a modest scale. The plasma composing the jet interacts with the surrounding magnetic field, producing synchrotron emission, which is light generated not by an object's heat but by electrons spiraling around magnetic field lines at relativistic speeds. This light is detectable at radio wavelengths, and it was exactly through this emission that astronomers discovered these objects' existence long before understanding what produced them. Radio galaxies, quasars, blazars, all are manifestations of the same fundamental process viewed from different angles and distances. The scale of destruction these jets can cause inside the host galaxy is hard to translate without comparisons. The jet crosses the galaxy like an energy beam. The interstellar gas structure simply can't absorb orderly. The gas encountering the jet is heated, compressed, pushed sideways, and in many cases expelled beyond the galaxy. A galaxy losing its gas loses its ability to form new stars. Not immediately, because residual gas remains for some time, but progressively as reserves deplete and aren't replenished. The black hole, by growing vigorously, ended up destroying the conditions allowing its own galaxy to continue growing alongside it. There's a structural irony here the universe seems not to notice. The same process building the black hole at prodigious speed during intense accretion phases is the process eventually collapsing the matter supply feeding this growth. Feedback isn't an elegant control mechanism, it's more like a fire consuming fuel around it until the environment can't support the flames anymore. The stabilization following isn't planned. It's the result of the system transforming itself until it can no longer sustain previous processes. The James Webb Telescope made it possible to observe these processes in galaxies so distant, the light reaching us left when the universe had a fraction of its current time. In some of these observations, it's possible to see galaxies in intense star formation states, while their nuclei already show clear quasar activity signs. The central black hole is in intense mode, while the surrounding galaxy still manufactures abundant stars. This coexistence lasts only while feedback hasn't reached star-forming regions with enough intensity to suppress them. When it does, the sequence of events following is recorded in galaxies we observe in intermediate states, like photographs of a process lasting tens of millions of years, but which we can compare by observing different objects at different stages of the same trajectory. Humanity learned to measure these phenomena in layers. Each light wavelength reveals a different layer of what's happening. Radio emission maps the jets and plasma lobes they form when losing speed encountering the extragalactic medium. X-ray emission reveals superheated gas closest to the black hole and regions where plasma shocked against interstellar gas structures. Infrared emission, James Webb's specialty, penetrates the dust-covering active galaxy central regions and allows seeing the accretion disk and circumnuclear regions geometry with clarity no previous telescope achieved for objects at these distances. But measuring isn't the same as predicting, and attempting to predict these phenomena reveals exactly how incomplete current understanding still is. The model's cosmology built to simulate galaxy formation and evolution must include some form of black hole feedback to produce simulated universes resembling the observed universe. If models run without this feedback, simulations produce galaxies much more massive than those existing, because nothing interrupts gas conversion into stars. Feedback exists in models as a structural necessity, a requirement of correspondence between simulation and observation. But details of how it works, what precise mechanisms are, on what timescale they operate, with what efficiency they transfer energy from nucleus to outer regions, these details are still being discovered and disputed. One of the most persistent dynamic structures the intense mode produces are radio cavities, also called plasma bubbles. When a relativistic jet propagates beyond the galaxy and eventually loses speed interacting with the hot intracluster medium gas, the plasma doesn't simply stop, it expands laterally, inflating a low-density, high magnetic pressure plasma bubble embedded in the surrounding hot gas. These bubbles are invisible at optical wavelengths, but reveal themselves in X-rays as dark regions within the diffuse heated gas glow. In radio telescopes, they shine intensely due to the synchrotron emission of their composing plasma. What makes these structures especially relevant is they persist for times much longer than the jets that formed them. A jet might have been inactive for tens of millions of years, but the bubble it created is still present, still slowly expanding, still transferring energy to surrounding gas via pressure waves propagating like extremely slow motion sound waves. This energy heats the intracluster medium gas and prevents it cooling sufficiently to precipitate a new matter rain toward the center. It's a heating mechanism operating on hundreds of millions of year timescales, sustained by energy injected during an already past activity period. Entire galaxy clusters can be maintained in a high-temperature state by this mechanism. The hot gas permeating the space between cluster galaxies would, without additional heating, have a cooling time estimated at less than the universe's age for the densest regions. It should have cooled and fallen to the center by gravity, forming a cooling flow feeding massive star formation in central galaxies. But that isn't what we observe. What we observe are clusters with stable hot gas, without expected cooling flows, and with plasma bubbles revealing past activity of the dominant cluster galaxy's central black hole. The black hole heated the gas, and continues heating cyclically whenever gas starts cooling and a new accretion episode is triggered by colder material falling. While you rest, somewhere at a distance light would take longer to cross than the entire history of complex life on Earth. A black hole that had gone through a period of relative containment has now crossed that threshold. The spiraling gas arrived in greater quantity than the system could process at the previous pace. The accretion disk reorganized its geometry. The magnetic field, already present but until then insufficiently organized to channel energy coherently, found the configuration transforming chaotic flow into direction. The first signals of the nascent jet will still take eras to cross the galaxy itself, but the process began, and what it will reorganize along the way is already present, waiting in the gas geometry, in the filaments composing the galaxy's structure, in the clouds still believing they will become stars. The asymmetry between the scale these processes operate on and the scale humanity observes them at creates a fundamental limitation no telescope can completely resolve. We observe states, not complete trajectories. We see a galaxy with active jets and infer past and future from examples of other objects at other stages. The narrative we build about how black holes enter intense mode, how jets form, how they interact with the galaxy, how eventual feedback cools the system. This narrative is assembled like an archaeologist assembles a civilization's life from pottery fragments found in sediment layers. Each fragment is real. The assembly is an inference disciplined by what we know about physics, but it's still an inference. What James Webb added to this archaeology is access to older epochs with unprecedented resolution and sensitivity. Galaxies that were previously just light points in survey images now reveal substructure. Nuclei previously indistinguishable from the galaxy's general glow are now isolatable and spectrally analyzable. Spectra revealing gas speed and temperature in different regions can now be obtained for objects existing when the universe was less than 1 billion years old. And what these spectra show is changing expectations cosmology built over decades of observation at less penetrating wavelengths and less extreme distances. The most disturbing phenomenon this axis revealed is the number of galaxies already massive and already having their black holes in high activity states when the universe was too young for this to be possible by previous models. They aren't rarities. There are enough that statistically they represent a significant population. And the population challenging the model isn't an anomaly to be discarded. It's a sign the model is incomplete somewhere fundamental. The incompleteness might be in primordial black hole growth mechanisms. It might be in gas cooling mechanisms in ancient epochs, which might have been more efficient than models assume. It might be in accretion physics at very high rates, which isn't as well understood as moderate rate physics because we lack sufficiently well-observed nearby analogs to calibrate models. It's likely in some combination of all these elements, plus some not yet identified. What becomes clear, the more James Webb deepens access to these ancient epochs, is that the dramatic phenomena the most intense part of black hole activity produces aren't isolated episodes in an individual galaxy's history. They are nodes in an influence network propagating. The galaxy being reorganized by its central black hole's feedback isn't just being altered internally, it's interacting with the surrounding medium, with neighboring galaxies, with filaments connecting it to the larger structure it's embedded in. The plasma its jets expel eventually encounters this structure. The energy it radiates heats gas at distances beyond its own limits. What happens in its nucleus doesn't stay in its nucleus, and this influence propagation is exactly what begins to be perceived when James Webb data is mapped not on the scale of individual galaxies, but of groups and clusters, and the even larger structures these clusters exist in. The dramatic phenomena of an individual point radiate outward, and upon radiating encounter other points having their own processes, their own histories, their own gas and darkness geometries. What they produce together is different from what any of them would produce in isolation. The filaments connecting galaxies to each other aren't just passive structures where matter slowly flows. They are living interaction channels, and when James Webb data is overlaid on existing dark matter distribution maps, what emerges is a picture of constant communication between nodes that seemed isolated. The galaxy having its central black hole in full activity is sending energy outside itself, and this energy doesn't dissolve into the void. It encounters the gas filling the space between galaxies, the so-called intergalactic medium, which is hot enough to be invisible to most telescopes, but which James Webb can detect indirectly via how it affects light crossing its extent. This heated gas doesn't return to its previous temperature. It remains hotter for periods extending tens of millions of years, and this elevated temperature prevents the gas from condensing again, from falling toward neighboring galaxies, from feeding new star formation elsewhere that would have no direct relation to the galaxy initiating the process. There's a main partner in this influence dance here, and it's the galaxy cluster itself. A cluster isn't a larger galaxy. It's an entity different in nature, a collection of hundreds or even thousands of galaxies held together by the gravity of an immense amount of dark matter and immersed in a diffuse, hot plasma filling the space between them. This plasma, called the intracluster medium, is one of the universe's most energetic environments. It shines in X-rays with an intensity reflecting temperatures of tens of millions of degrees. And it's exactly in this plasma that the jets of the cluster's most massive black holes deposit their energy most dramatically and consequentially. When James Webb observes clusters existing already in the universe's first billion years, what is seen is this plasma being stirred, structured, compressed, and expanded in ways revealing the influence of multiple active black holes simultaneously, each contributing its jets and radiation to the thermal state of a gas ocean, serving as a reservoir for all the cluster's future star formation. The energy exchange between an active black hole and the cluster plasma works in a way physicists describe as a cosmic thermostat. When the plasma around a galaxy's nucleus cools below a certain threshold, gas begins falling toward the black hole. This falling gas feeds the accretion disk, which increases the active nucleus's luminosity, which in turn sends more energy outward as jets and radiation, which heats the surrounding plasma, which interrupts cooling, which reduces the amount of gas falling on the black hole, which reduces nucleus activity, which allows the plasma to start cooling again, initiating the cycle anew. This mechanism isn't speculative. It was directly observed in nearby clusters, like the Perseus cluster, where X-ray images reveal plasma cavities created by the central black hole's jets, pressure waves spreading through the intracluster medium like waves on a pond, and temperature variations corresponding exactly to what the model predicts. James Webb is now showing this same mechanism was already operating when the universe had only a fraction of its current age. What makes this feedback cycle particularly fascinating is the timescale it operates on, and how that scale changes depending on the period examined. In the young universe, when black holes were growing rapidly and available gas was abundant, cycles were more violent and faster. An intense accretion episode could last tens of millions of years, and the released energy was enough to alter gas states in regions extending hundreds of thousands of light years. But this same violence was also the germ of its own moderation. The more energy the black hole deposited in the surrounding medium, the harder it became for that medium to provide new gas. The cycle became slower. Activity episodes became separated by relative quiescence periods lasting hundreds of millions of years. And over time, as the universe expanded and available gas became less dense, intense activity episodes became increasingly rare and increasingly mild. In terms of human decades, what is observed of any specific active black hole seems almost static. An active nucleus in full activity today might seem practically identical decades later. Variations occurring on this timescale are subtle, light fluxes oscillating around a mean value, small jet intensity fluctuations only becoming noticeable when compared across repeated observations. To any human observer, a bright quasar in the sky is a constant, something born and dying only on the scale of instruments becoming more sensitive across generations. But this apparent stability is misleading. What seems motionless on a decade scale is changing irreversibly on a century scale and transformatively on a millions of years scale. On a century's horizon, the jet a massive black hole is emitting right now will have traveled distances still invisible to any telescope today. The jet's front will encounter intergalactic medium regions not yet perturbed, and the shock between the jet plasma and the gas it encounters will create new structures, radio emission lobes potentially larger than the galaxy that created them. The pressure waves these shocks send outward will eventually encounter neighboring galaxies, compressing gas in their peripheries, potentially triggering small star formation waves in regions otherwise remaining quiet. A galaxy a few million light-years away might have its star formation rate altered by an event occurring in its neighbor at a time when the affected galaxy didn't yet exist in its current form. On a millions of years scale, What was an active galactic nucleus might have become completely silent. The black hole fueling the quasar is still there, more massive than it was, but deprived of fuel by the very energy it released. The surrounding galaxy underwent a profound transformation. The gas it had was consumed in stars or expelled by the winds the quasar generated. Without gas, no star formation. Without star formation, the young blue star population giving the galaxy its characteristic brightness disappears, progressively replaced by older, redder stars shining less intensely but lasting much longer. The galaxy ages. It doesn't die but transforms into something different from what it was, carrying in its structure the scars of a violent youth readable only by those knowing how to look for the right signs. James Webb is being that scar reader. When it points to galaxies existing over 13 billion years ago, it isn't just seeing ancient galaxies. It's seeing the ancestors of systems we know today and showing us that what transformed them was present from the beginning in their nuclei, in those black holes seeming too large for the age of the surrounding universe. And what is read in these images is a story of sensitivity to initial conditions having a beauty and disturbance simultaneously. Sensitivity to initial conditions is a concept appearing in very different contexts, but acquiring a particular cosmic weight here. A galaxy forming in a slightly denser region of the early universe had access to more gas, which fueled a more massive black hole, which in turn expelled more energy, which suppressed star formation earlier, resulting in a galaxy that by now is a red quiescent system dominated by old stars. A neighboring galaxy, forming in a region just slightly less dense, had a black hole growing slower, which didn't expel enough energy to completely suppress star formation, which is still forming stars today. These two galaxies, starting as nearly identical fluctuations in the early universe's density field, reached radically different states because initial conditions had a minuscule asymmetry time amplified disproportionately. This imposes fundamental limits on what human prediction can achieve, not technological limits which could be overcome with better instruments or more data. Principal limits born from the system's own nature. A slightly different set of initial conditions produces an evolutionary trajectory diverging from the first progressively and then dramatically. To predict such a system's final state accurately, it would be necessary to know initial conditions with precision exceeding any possible measurement, because any measurement has uncertainty, and this uncertainty is enough for trajectories to separate beyond any tracking capacity before reaching the final point we want to predict. The universe guards its secrets not from lack of data, but from a mathematical structure transforming small ignorances into large surprises. And yet, within these prediction limits, there is an order simultaneously comforting and astonishing. The same physical laws making long-term behavior unpredictable in detail produce statistical patterns predictable in aggregate. We can't say which specific galaxy will have its black hole reactivated in a given period, but we can say precisely that a certain fraction of galaxies of a certain mass at a certain epoch will show nuclear activity. We can't trace a single gas grain's path from the intergalactic medium to a black hole's event horizon, but we can describe the average rate gas falls into black holes of a certain mass in a certain environment density. Statistical physics transforms individual unpredictability into collective regularity, and it's in this regularity theoretical models find their validation in James Webb's observations. There's something profoundly beautiful in this tension between the particular and the universal. The black hole at the center of the brightest galaxy in some distant cluster James Webb is observing right now is a unique object with a history not repeated anywhere else in the universe exactly the same way. Its current mass is the product of a series of mergers and accretion episodes following a sequence chance shaped as decisively as physical laws. And simultaneously it obeys the same equations describing the closest and farthest black hole, the most massive and least massive. It is singular and universal at the same time, like every living being in a biosphere, like every star in a galaxy. When James Webb data arrives at processing centers where astrophysicist teams analyze it, what they see on screens aren't just light points and emission spectra. They are compressed versions of stories lasting billions of years, stories where main characters are objects not even having surfaces, existing as space regions where reality's geometry folds on itself in ways our everyday intuition can't imagine. And yet, the data makes sense. Galaxies appear where models predicted they would appear, at least in general characteristics. Black holes have masses the feedback mechanism suggests they would have. Quiescent galaxy spectra show signatures of stellar populations formed in a brief, intense period, as feedback suppression models predict. This agreement between prediction and observation is how science confirms it's on the right path. But it's never perfect, and imperfections are as important as agreements. The massive galaxies James Webb found in the universe's first 500 million years don't fit existing models. They are too large, formed too early, with black holes growing too fast. These discrepancies aren't errors to be corrected and discarded. They are windows, points where the universe is saying human understanding hasn't yet reached a complete description, that there's something in very ancient galactic formation, processes models haven't yet captured correctly. And it's exactly in these windows the most fascinating work happens. When an observation doesn't match expectations, it opens a possibility space. Perhaps star formation in the early universe was more efficient than thought, converting gas into stars at a rate modern models don't reproduce. Perhaps primordial black holes had a different origin than massive star collapse, perhaps forming directly from entire gas cloud collapse in a single step without the stellar intermediate. Perhaps dark matter has properties not yet incorporated into galactic formation models, properties affecting how first structures condensed and grew. Each of these possibilities is being investigated, and James Webb is providing data that will eventually decide which approaches reality closest. There's a contemplative dimension in this investigation process going beyond scientific research mechanics. When looking at a James Webb Deep Field image, where thousands of galaxies fill a sky fragment smaller than a coin's appearance at arm's length, what is felt isn't just admiration for the technique making this image possible. It's something closer to what is felt before any vast serene landscape, an expansion of proportion sense, a perception that the space we exist in is immense, in ways exceeding any language's capacity to fully transmit. And within this immensity, each light point is a complete system in itself, with its history of violence and quiet, of creation and suppression, of black holes existing before the galaxies containing them today. The universe's rhythm is different from the human rhythm. Where we perceive immobility, there is movement too slow for our senses. Where we perceive chaos, there is statistical order revealing itself only when looking at the whole. Stars dying in supernovas and galaxy mergers lasting hundreds of millions of years are violent events on a timescale, making them invisible to direct experience. And black holes pulsing in their accretion and quiescence cycles, alternating between febrile activity and deep silence periods, follow a rhythm no human life can witness from beginning to end. But it's possible in a way to learn to feel this rhythm. James Webb images are like photographs of a dancer taken in extremely long exposures, where movement doesn't appear blurred but as a smooth line traced in space, a path the form traveled. Each galaxy the telescope captures is a billions of years long exposure, compressed into a set of photons reaching the telescope mirror and recorded on a detector. The movement is there, encoded in the galaxy's structure, in its star's age distribution, in its gas-chemical composition, in how its central black hole relates to the system's total mass. And the more one looks, the more one learns to read these codes, the more what seemed a disconcerting diversity of forms and processes begins revealing a profound coherence. Systems seeming to have completely different trajectories share the same transitions, the same thresholds, the same qualitative change moments. The galaxy suppressing its star formation 10 billion years ago and the galaxy doing the same right now go through the same process mediated by the same mechanism. The central black hole responding to available gas and returning energy to the surrounding medium. The scale changes, details change, but the process structure is the same. This unity beneath diversity is what scientists call universality, and it's one of the most surprising things physics discovered about nature. Very different systems composed of very different elements, subject to very different interactions, can exhibit the same collective behaviors when near certain critical transitions. The transition of a black hole from a quiescent to an active state has mathematical characteristics also appearing in completely different phenomena, in phase-changing materials, in oscillating biological populations, in learning neural networks. The process's abstract structure is shared by domains the surface radically separates. This perception doesn't diminish astonishment before the universe. On the contrary, it deepens it. Discovering a pattern appearing in a distant galaxy also appears in other contexts doesn't make the galaxy less extraordinary. It makes the pattern more extraordinary, and it makes reality as a whole more coherent, more interconnected, more like something having a structure going beyond each physical domain's particular accidents. Behind all the complexity of interactions between black holes and galaxies and clusters and filaments and the intergalactic medium, there is something connecting processes to each other in a way James Webb data is beginning to illuminate in ways previous telescope generations couldn't reach, something simple organizing everything, present from the beginning, persisting through all transformations. Feedback is one of the most silent yet most powerful concepts physics knows. It isn't a single event, isn't an isolated cause producing an effect and ending its role. It's a process folding on itself, using its own result as new raw material, transforming each consequence into renewed cause. And when looking at the relationship between black holes and galaxies through James Webb data, what we see isn't a linear event chain, but a web of intersecting feedbacks, amplifying, balancing, and transforming over billions of years of cosmic history. The most immediate feedback, the most visible in the light spectra the telescope captures, is that which the black hole exerts on surrounding gas. When matter falls toward the event horizon and forms an accretion disk, the energy released by this process is colossal. Part of it escapes as radiation crossing surrounding gas, ionizing it, heating it, and potentially pushing it out of the galaxy's central region. Part escapes as relativistic jets extending for distances rivaling the galaxy's own size. These jets and this radiation reach gas that could otherwise slowly cool and collapse to form new stars. And upon arriving, they perturb this process, they hinder collapse, they reduce star formation. The black hole, by growing, restricts the raw material stars would use to be born. This negative feedback, this suppression mechanism, explains something astronomers call quenching, a dimming of stellar activity in massive galaxies. The giant elliptical galaxies we see today, vast and reddish, full of old stars and almost devoid of new star formation, are galaxies that went through this process. They had intense stellar activity periods, grew their central black holes, and then black hole feedback progressively silenced the star formation engine. James Webb is finding galaxies in this dimming process at much older epochs than expected. Galaxies already looking old, quiescent, without significant activity, at times when the universe was less than 1 billion years old, which implies the growth and suppression cycle might have occurred much faster than models predicted. But feedback isn't just suppressive. There is also positive feedback, a mechanism amplifying growth instead of restricting it. When black hole jets cross the interstellar medium, they can, under certain conditions, compress gas along their path in a way favoring collapse. The perturbation the jet causes can create high-density regions that, instead of dispersing gas, concentrate it locally. Stars can be born precisely in regions the jet crosses, a phenomenon astronomers call jet-induced star formation. The same process suppressing star formation in certain contexts can stimulate it in others. The difference lies in local conditions, in gas density, in temperature, in the geometry of the encounter between the jet and the medium it finds. This feedback duality, the same process's capacity to produce opposite effects depending on local conditions, is one of the reasons galactic evolution is so hard to model and so rich in surprises. James Webb data is revealing this duality in concrete galaxies, observed at specific moments in their history. In some, the central black hole seems to be actively suppressing star formation, with spectroscopic signs of hot gas fleeing, of galactic winds carrying matter out of the galaxy. In others, signs point to the opposite phenomenon, with star formation regions concentrated precisely along structures the nucleus activity seems to have shaped. Reality is more complex, more nuanced, fuller of intermediate cases than any simple model could capture. The chemical dimension of this story is, in itself, grounds for profound contemplation. When the first stars were born in the primordial universe, the cosmos was chemically naked. There was hydrogen, there was helium, there were lithium traces, nothing else. The periodic table, with all its element richness, was almost empty, every element heavier than helium, everything chemists colloquially call metal, had to be forged inside stars accumulated over generations of stellar life and distributed through the intergalactic medium through these stars' deaths. And here the connection with black holes becomes profoundly molecular. The massive stars living short lives and ending in supernova explosions are exactly the type of star forming most easily in high-density environments, in the star formation bursts characterizing rapidly growing young galaxies. These stars produce heavy elements in abundance, and when they explode, disperse this material through the interstellar medium. The gas falling back toward the central black hole is already chemically enriched gas, different from the primordial gas fueling the first generations, and stars born from this second enriched gas generation have different properties from the first, with more diverse planet populations, with organic chemistry possibilities the primordial universe simply didn't have. The James Webb Telescope, thanks to its unprecedented spectroscopic sensitivity, is beginning to map this chemical history in distant galaxies. The spectral lines it detects don't just speak of temperature and speed, they speak of composition. They speak of which elements are present, in what proportions, in what physical states. And by comparing the chemical composition of galaxies at different epochs, astronomers are reconstructing the cosmic enrichment history of how the universe progressively became chemically more complex, of how life's ingredients were synthesized and distributed over billions of years of stellar and galactic evolution. Black holes have a role in this cosmic chemistry going beyond simple gravitational catalysts. The extreme conditions around an active black hole, with intense magnetic fields, with intense radiation at all frequencies, with high-energy particle winds, create an environment where physics and chemistry interact in ways we don't yet fully understand. The molecules existing in gas clouds near a galaxy's active nucleus are different from molecules existing in a quiet galaxy's tranquil interstellar medium. Molecule photodissociation by intense radiation, gas ionization by accretion disk X-rays, molecular cloud compression by active nucleus winds. All this creates unique conditions for extreme chemistry terrestrial laboratories can't replicate. The systemic view emerging from all this is of a cosmos not being a collection of isolated objects, but a network of interconnected processes, each influencing others through multiple space and time scales. A black hole at a galaxy's center influences gas a few light years away and also influences through its jets gas in regions hundreds of thousands of light years away. A galaxy influences neighboring galaxies through its gravity, through gas exchanges, through mergers and perturbations. Galaxy clusters create conditions in the intracluster medium affecting each galaxy within them, and the cosmic web's great filaments channel gas and dark matter from vast universe regions toward nodes where galaxies concentrate. In this system, James Webb is revealing black holes aren't just products of galactic evolution, objects growing passively while galaxies develop around them. They are active agents, participants actively shaping their host's structure and destiny, and this agency is older than thought. The discovery that supermassive black holes existed before the galaxies around them took shape is forcing a profound revision of how we understand causality in this system. But beyond direct causality, there is something even deeper these data are suggesting. There is emergence. In complex systems, patterns and properties arise from simple rules interacting at scale, and these emergent patterns are qualitatively different from the rules generating them. A galaxy's complexity, with its spiral arms and stellar populations and gas structure and central black hole and formation and evolution history, isn't contained in any individual laws governing gravity or plasma or thermodynamics. It emerges from these laws' interaction under specific conditions over sufficient time with the right perturbations. Black holes in the early universe are extraordinary examples of accelerated emergence. From a simple perturbation in the primordial universe's density field, from a slightly denser region collapsing under its own gravity, emerges a sequence of increasingly complex structures. Stars, star clusters, protostellar galaxies, and at some point in this sequence, black holes growing at a speed defying our understanding of the possible. Emergence isn't only smooth and gradual. It can be rapid, almost explosive, with complex structures arising on timescales much smaller than underlying processes would suggest. And here we reach the synthesis. Deep down, the story James Webb is telling us about black holes and galaxies is simply the story of how gravity organizes complexity. This is the unifying principle reconnecting all elements we explored throughout this journey. Gravity is the force collapsing the uniform into structured, transforming homogeneity into difference, creating density gradients allowing more complex processes to occur. It's the force gathering primordial hydrogen into stars, that gathered stars into galaxies, that gathered galaxies into clusters, that concentrated matter in galaxy nuclei to the point of creating singularities. But gravity alone doesn't tell the whole story. What James Webb is revealing is that black holes aren't just extreme gravity concentrations. They are radical transformation points, where matter enters and doesn't return, where energy is released with efficiency incomparably greater than in any other process the universe knows, where spacetime acquires curvature so intense the very notions of inside and outside, of before and after, become problematically ambiguous. And it's exactly this extreme transformative capacity making black holes such powerful evolutionary agents. They don't just accumulate, they transform and transmit the effects of this transformation to the surrounding environment. the relationship between black hole mass and host galaxy properties, which previous observations established for nearby galaxies, is now being tested in extreme time and mass regimes. And what James Webb is showing is this relationship exists, that it isn't an accident of recent universe epochs, but seems to be a fundamental characteristic of how black holes and galaxies co-evolve, even when this co-evolution begins much earlier than expected and progresses at a speed we don't yet know how to fully explain. The correlation is the sign gravity organized complexity consistently, in a way producing similar patterns under diverse conditions throughout observable universe history. The cosmic web filaments we explored, the nodes where galaxies concentrate, the clusters where galaxy interactions accelerate processes otherwise taking longer, the galaxy mergers perturbing orbits and feeding central black holes. All this is gravity organizing complexity on progressively larger scales. And black holes are the local catalysts of this organization process, the points where complexity concentrates most intensely, where feedbacks are most powerful, where effects propagate furthest. The first stars we discussed, those massive population 3 stars living brief lives and dying in spectacular explosions, are part of the same narrative. They were gravity putting the universe in order for the first time on a stellar scale, creating the first thermodynamic gradients intense enough to forge heavy elements and distribute them through the cosmos. And when some of them collapsed into black holes encountering their neighbors and growing, it was gravity advancing to the next organization scale, building the catalysts accelerating everything coming after. The light James Webb captures from extremely high redshift galaxies is, in the ultimate sense, gravity being recorded. It's gravity that, over hundreds of millions of years, organized gas and dark matter into structures complex enough to emit that light. It's gravity that, by concentrating matter in those galaxies' nuclei, ignited the quasars illuminating the early universe with a brightness still today, billions of years later. Reaching the golden mirrors of this extraordinary instrument, humanity placed in a gravitational equilibrium point between Earth and Sun. Looking at James Webb images is looking at gravity working on a cosmic scale. It's seeing physics' simplest and most universal principle, the tendency of all mass to attract all other mass, produce, over sufficient time and under adequate conditions, structures of a richness and complexity no observer could deduce just from field equations. Emergence is there, in the interval between the simple rule and the complex result, and the telescope is the instrument with which humanity begins seeing this interval, with the resolution necessary to start understanding it. There's something profoundly peaceful in this understanding. The idea that the universe has a structure, that it isn't arbitrary chaos, but a system where simple processes produce progressive order, where complexity doesn't arise from nothing but emerges from principles permeating it on all scales, that black holes at galaxies' hearts and galaxies at cosmic web nodes and filaments connecting everything are different manifestations of the same organizing principle, that there is an underlying coherence to everything, and in this coherence rests something going beyond science, a feeling that reality isn't indifferent to order, that there is something in the fabric of what exists tending toward structure, producing patterns, creating conditions for complexity and, eventually, for the consciousness observing all this and wondering how it's possible it is this way. James Webb is an instrument, an extraordinary set of mirrors and detectors created by beings wondering about origins. But what it reveals goes beyond technical discoveries. It reveals we are connected to a process beginning long before us and continuing long after, that the atoms composing our body were forged in stars exploding billions of years ago, that black holes existing before surrounding galaxies shaped conditions, eventually allowing planets to form, organic chemistry to flourish, life to emerge. You are safe. The universe creating all this also created you. And the same gravity collapsing the first hydrogen clouds into stars, gathering stars into galaxies, building the filament web sustaining clusters, also sustains the Earth you inhabit. You are part of this system. You always were. Now images can begin dissolving. Distant quasars are softening their glow. Cosmic web filaments are becoming more ethereal, more like mist than defined structure. Galaxies become soft light points in the dark field. You are safe. The universe takes care of you the only way the universe knows how, creating conditions for you to exist, maintaining physical constants, making matter, time, experience possible. While you rest, black holes continue their slow dance with surrounding galaxies. They continue accumulating matter at incomprehensible paces. They continue sending jets shaping intergalactic gas. They continue being silent catalysts of cosmic evolution. You are part of this. You always were. Cosmic web filaments continue growing slowly, with a patience transcending any human scale. Galaxies continue moving, converging, drifting apart, following paths, gravity traces in space-time. Everything is in order. James Webb continues orbiting in space's cold silence, its golden mirrors cooled almost to absolute zero, its detectors recording the oldest light existing, its antenna transmitting discoveries to humanity's ears as data, becoming images, becoming understanding. You are safe. The universe is billions of years old. It always found a way. And you are here now, part of this extraordinary continuity. Stars above you continue shining. Most of them have a black hole in their distant future or already have an heir to one at the heart of the galaxy housing them. But now they shine with the serenity of who exists in the present, in the only moment existing, which is this one. Everything is in order. The universe takes care of you. Cosmos images are becoming softer. Black holes become just silence points in a light field. Galaxies become luminous sighs in the vast dark. The cosmic web becomes a tapestry you can imagine stretching infinitely in all directions while you rest. You are safe. You always were. While you rest, the universe continues expanding, taking each galaxy gently further from all others, in a separation dance so slow no civilization would ever perceive it if it hadn't built telescopes. A dance occurring in absolute silence, in a space where there is no air to transmit sound, only gravity and light and time. The universe continues its silent dance and we rest in its embrace. Thank you for walking with me tonight. Sleep well.